All right, so today I hope to finish up with binary search trees as well as covering briefly heaps, which are a form. They're still trees, but they have a little bit of different application. So remember, we are on Piazza. If you have any questions, go ahead and post there. Last time we did the search and the insert methods, right? And we actually implemented those. I believe, right? We implemented them by getting the parent of the element, and then inserted the new child as that parent where it should be, basically. If you look at this, if you look at a typical binary search tree, of course, searching is easy. All you have to do is start at the root, and if the thing that you're looking for is less, you go left. If the thing that you're looking for is greater, then you go right. If you find what you're looking for, great. If you don't find what you're looking for, then it results in a unsuccessful search. But if you were to insert something, like say 55, you would have the same procedure, that you would do a basic search, and then you would find, oh, well, if 55 existed, it would be here. And with an unsuccessful search, then of course you can go ahead and insert it as the new child. The way that we did that is by getting the parent node of where it should be. And making a choice of if it's already there, then we're not going to allow duplicates, and so we end up not adding it. Otherwise, we end up adding it as the left child of the parent node, or if we were inserting something like 101 as the right child of the parent. And we did that by implementing this get parent of method, and then using it in our insert method. And all we had to do was determine should I be a left child or should I be a right child. And I set the parent and I set the child appropriately, right? We did all that last time. But what about now deletion? And in fact, I don't even think that we developed the algorithm last time in this section. So let's develop that now. Suppose that you wanted to delete, say, 48. Delete 48. Well, what's the first thing that you've got to do? You got to find it first, right? So a binary search, right? And you end up finding it. If you end up not finding it, no operation. Throw an exception, return false, right? I didn't end up deleting it, right? Do whatever you're going to do as far as the design choice goes. But if you do find it, then what do you need to do here? In this particular case, how do I delete 48? By making its parent node point to null, in which case we end up basically erasing it from existence. Okay? Well, that works out. What if we want to delete, say, 60? Can I just, okay, well, I find it. Can I just go ahead and delete it? I would end up losing this entire branch, wouldn't I? So, what do I need to do to get rid of 60? What? Yeah, so in this particular case, I can just go ahead and make it so that 50's new right child is 90. 60's old right child. Right? Okay. That works out. What happens if I want to delete, say, 50, though? Well, I could do the same trick, but that trick won't work if I had inserted 55. Now I've got two children, right? If I try to make 60 the new root, then it has 1, 2, 3 children. And is that a binary search tree? That's not even a binary tree. I can make 40 the new root, but again, it'd have 1, 2, 3 children. All right, so again, 55 hanging off of here. I can't do anything as far as like promoting one of the children or something like that, or one of the direct children. So instead, let's do something else. Let's just go ahead and clear it out. Right? Now, 50 is gone, right? But we have this gap in our tree, right? We've split our tree into two trees. I don't want to do that. I don't want to change the topology of my tree. So let's focus on the left subtree here. And I can't promote 40 up because, again, I would have 3 children. What can I promote up here in this tree all the way up to the root so that the binary search tree property is satisfied? Remember, everything in the left subtree has to be less than this root right here. So that would mean that I could promote what? 48? Nope, what? 49 is greater. And so I would have to put 49 up here. Once I've done that, then I can get rid of 49, right? And I know how to do that, right? By making 45 or 48 45's new right child. Okay. What's another alternative that I could have done? Okay, let's put that another way. Let's focus on the right tree here. What among this could I promote up and still preserve the binary search tree property? 55. Now, what is it about 55? It's the smallest among the things that are greater, right? What was it about 49? It was the greatest among things that are smallest, right? I have a choice. I could do one or the other, or I could randomly pick each time, or just always go to the left and then find the maximum or something like that, right? The problem, though, there's still a problem, right? What happens if I've got a maximum here, and it has two children, a left child and a right child, right? So remember, I'm in the left subtree, and I find the maximum, but it still has two children. Yeah, why would the maximum have a right child? Remember, binary search tree property, R would be greater than max. And therefore, you don't have the maximum. Keep going right, keep going right, keep going right, until there's no right child. Right? And if there's no right child, then that's the maximum. And we know how to deal with that, because if it has 0 children, it's like 80, say 85, then we don't need to do anything, right? We just delete that node and trim it off the tree entirely. If it only has 1 child, like 15 here, only has 1 child, we know how to deal with that by simply just circumventing that node. So the only one that we don't know how to deal with is when it has 2 children, and then we can use a combination. Replace it with the minimum or the maximum among the things that are less, or the minimum among the things that are greater, and you know that whatever that minimum or the maximum is only has at most 1 child, and we know how to deal with that. All right? Great. Now we've got an algorithm. Let's go ahead and put it into action. Okay? So I've got a method over here started. Delete the element t. Well, the first thing that you've got to do is what? Find it, right? And I already made a method up here called find node of, right? And then I refactored the contains method to simply use that. Remember, this one returns the tree node, and I made it private so that I don't have a leaky abstraction. You should not allow access to the internal workings or structure of your data structure to the outside world. Making this public would mean that I'm exposing all of my tree nodes, right? From the outside world, it's just a thing that I can put stuff in and search for stuff and take stuff out, right? With your sorted list, are you going to be doing an array-based list? Are you going to be doing a linked list? Are you going to be doing a tree, right? Are you going to be doing something else entirely? I don't know. I don't care. I just need to know the interface. How do I put stuff in? How do I take stuff out, right? Or find stuff or whatever. So I made this find node of, and once it finds the node of the needle, then it simply returns that whether or not it was null or a success. I did find it, right? And it returns the current if it finds what it's looking for. Otherwise, if it goes through the entire search process and doesn't find anything, then it returns null. Okay? All right, so delete. Find node of, tree node. We need to delete this node, right? Find node of element, right? And of course, you know, if it's null, then we can return immediately, right? If node is null, then return, right? And I've made this into a void function. It's no operation, right? You want to delete something doesn't exist, okay, go on with your life, right? Or what we could do is we could use this return value here to indicate that, nope, your call to this function had no effect. Right? And now we're communicating more information, and more information is always more flexible. If we wanted to, we could throw an exception, right? That seems a little bit harsh though, right? To me, right? Anyway. So, otherwise I'll return true down here just so that it compiles and we can actually work with it, okay? How do I know? Oh, so let's take care of these cases. What if they've got no children? If the node has no children, dot, 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 then what do how do I do this? Well, first of all, how do I determine if it has no children? If the node dot has right child, has left child, not, right, not both of those things in and, right? Or what I did is, before I came here, I refactored this to add a little bit more convenience functions, right? If you ever find yourself writing out this convoluted and long logic, and that logic deals with, say, a tree node, where does that logic belong? In the node class, right? So, for example, am I a left child? Am I a right child? All I have to do is ask my parent. My parent, your left child, is that me? My parent, your right child, is that me? Right? Get number of children. Initially, there's 0. If it has a right child, then there's 1 more. If it has a left child, then there's 1 more. And I return that result, 0, 1, or 2. And so all I need to do is use that now, right? Dot. Actually, if it has no children, we have another convenience function that's even more direct. If it has no children, it's known as a what? As a leaf, right? If it's a leaf, then I simply delete it. How do I delete it? Here again is the picture. If it's a leaf, like say 12, what do I need to do? Yep, go to my parent and say, if I'm a left child, then delete your left child by setting it equal to null. If I'm a right child, say 28 here, then I go to my parent and I say delete your right child by setting it equal to null. Right? Now, 12 here refers to a parent. Do I need to really worry about that? Once it's been cut off from its parent, then it doesn't matter if it's referring back up here, right? Java will take care of it. Java will clean up after itself. If this were a language like C or C++, you would definitely have to take care of both directions and call free and whatever else you need to do to make sure that you are doing memory management on your own. But Java, convenient, we don't have to do that. Like 85 is a leaf.
Well, yeah, but like, what if
We'll get to the other cases here in a second. Right? So if it's a leaf, I just need to tell my parent if I'm a left child is left child. If I'm a left child, I need to tell my parent, node.parent dot, all right, get parent, fine, set left child to null. Right? Else, there's only one other possibility. I'm either a left child or a right child, so node.getParent.set right child to null. Okay, that's the easy case. Else if node.get num children is equal to 1. Now there's only one child, right? So I don't know if it's a left child or a right child though, right? So all I need to do is ask, right? If node dot has left child versus else if node has a dot right child, but we already know that that's the case, so I'm just going to go in else here. All right, so I'm deleting the node, the number of children is 1, and that child is a left child. So how do I end up deleting it? In this case, for example, do I not have any example? Oh, 49, right? I'm deleting 49. It has one child, and that child is a left child. So how do I make it so that 45 is now referring to 48? Well, I've got more cases, right? If my parent dot, or actually no, I'm not even going to go to the parent because I've got those convenience methods. If I am a left child, is left child, then what do I do? So let's understand. So there's one child. It's the I am the left child. Oh no, wait. I have a left child. I have a left child, and I am a left child. So I need to set my parent's left child to my left child. So node dot get parent dot set left child to my left child, and you're done. Right? And then there's another else condition here. Otherwise, what's the other condition? I am a left child, or I have a left child, but I am a right child. This is where comments come in nice and handy, at least initially. I am node is a left child and has a right child. So make my parent's left child. Oh wait, node is node is a right child. Sorry, right child, and has a. Oh yeah, okay. So do I even need an else here at all?
Yes, because note is left and note is right, but the parent,
Yeah,
the child, note doesn't matter.
The other one would be when you're right child.
I think we're too confused here. All right, so let's start over here. If the node has a left child, so if the node has a left child, let me just write it out over here. So here's the node. Node. I could be a left child or I could be a right child. Right? There's the parent. There's the parent. And I have a left child or I have a right child. It would matter, wouldn't it?
It would. No, it should be created with the parent all the time.
Well, yeah, but I need to know which one to set it to. Right? I could probably take care of it by saying whatever the so if I'm a leaf. Wait. Okay, sorry. No, here. Let's reset this. So tree node t. We're going to simplify it by winnowing down the number of cases. So I have a number of children, which is 1. I just want my child, right? So child is equal to. Now, if my child is a left child, then I need to set this to the left child. If it's a right child, then I need to set this to the right child. So equals node dot get left child or node dot get right child. There we go. And node dot has left child. There we go. Okay. We've seen the ternary operator before, right? So this is basically a shorthand if then else. So if the node has a left child, then the child will end up being the left child. Otherwise, it'll end up being the right child. Okay? Now all I need to do is set my parent's left or right child to this child, right? Which is basically their grandchild, right? So if node dot is left child, then I will set my parent, node dot parent dot get parent dot set left child to the child, right? Otherwise, node dot get parent dot set right child to child. Right. And that greatly simplifies things because I took care of the logic instead of having if, else, if, like 4 different cases to think of, I collapsed 2 of those cases with this simple ternary operator right here. Right? All right, what's the only other case here? Oh, actually, I also need to take care of the parent, right? So child dot set parent to node.getParent, but that's going to be the same in both cases. So I'm going to promote that up here, right? So if you're not keeping track of parents, then you don't need to do that at all. But I am keeping track of parents here.
Would it be less confusing if we did it below the if-else condition?
I don't think so. I don't know if it does. If you want to, you set the child of the parent and then the parent of the child. Yeah. I don't know. I like to take this opportunity to share with you a nice little brain teaser poem or whatever, right? So we've got a parent-child relationship here, right? And we've got the case where they're an only child. And so what you're doing all over the place is you're getting the parent and setting the parent's child to that child, right? And you're setting the grandchild's parent to that parent, right? So you're making all these references that I'm jumping from you to parent just so that I can jump back to you, right? And there's a nice little brain teaser there where this guy walks up to this painting and he says, "I know this person," right? And he says in a little rhyme, "Brothers and sisters, I have none, but this man's father is my father's son." Who's in the painting? So you have to walk through it because it's, confusing. Brothers and sisters, I have none. I'm an only child. But this man's father is my father's son. So, brothers and sisters, I have none. So who's in the painting? Yeah, it's the man. It's a self-referential thing. And so that's what we've got here, right? I'm saying, brothers and sisters, I have none. I'm getting my parent, my father, and my father's son is right there, me. Right? It's all with respect to you. Right? I'm going to set this as a to-do. Right? How would I go about doing this when it has two children? 1, find the. We already found it because we want to have the node here, but find the what? Min of the right subtree, or the max. No, brothers and sisters, I have none, but this man's father is my father's son.
Yeah.
I'm referring to me, right?
Okay.
All right, so the min of the right subtree or the max of the left subtree. Right. Then delete that node. Extract the key value here and put it in this node. And I think that you'd have to make it more mutable. And I don't know if we have this mutable. Nope, we made this immutable, so we'd have to go back and refactor and make it mutable so that we can replace that node. But we know how to delete that min-max, right? It's right here, right? All we have to do is call this again, or put this logic out into another method and reuse it. So 2, delete the min-max and replace the value of node with its key. Right? What I want to do is just 1 here. Right? I'll leave the rest of it to you. How do we find the minimum or the maximum? Right? So I'm going to have another method here. Let's initially make it public. Tree node t get max. Get max, yeah. We'll go to the left subtree and then find the maximum in the left subtree. And to get to the left subtree, I have to have a starting point. I have to start with a node, right? So a tree node t u is what I'll call it. Oh, in fact, I'll call it current. No, I'll call it u. Right? Actually, I'll call it root. Subroot is an even better name. It's not the root of the tree, it's the root of a subtree. So for example, if I start at, say, 45, then I want to find the maximum of the tree rooted at 45. If I start at 50, then I want to find the maximum of the entire tree. If I start at 40, I want to find the maximum of the tree rooted at 40, right? Etc. So how do I go about doing that? If I just gave you this node right here, how do you find the maximum? Do a BFS, right? And then maintain a maximum that you found so far? Probably not. Pre-order traversal, post-order traversal, nah. What do I need to do with to exploit the binary search tree property? Just go right, go right, go right until you've fallen off the edge. All right? Okay. So, keep going right until you can go no further. Dot, dot, dot. All right? So, tree node, T, I'll call it current, and I'll start at subroot. And then I'll have some sort of a while condition here. Initially say while current is not equal to null. Then I will go right. So current is equal to current dot get right child. Likewise, if I were to search for the minimum, what would I do? Keep going left, 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 left until you can go no further. At that point, can I just simply return current? Nope. Why? Breaking out of that loop would mean what? The current is null, right? That's not what I wanted. I wanted the maximum. In fact, what I wanted is I wanted the max node. All right, so let's rethink this. One way I could do it is by keeping track of two things. A current, or a current and a previous. Previous and current. And then what I would do is I would update them throughout the entire process. And previous, current, so that when current falls off the edge of the tree, previous is still back here. And then I would end up returning previous, the maximum. Okay, that's one way. What's another way? Yeah, just stop early, right? While current dot has right child. Right? No need to even for null checks here. While it has a right child, go to it. The second that it does not have a right child, you're done, and that is the maximum node. Now, let's rethink this. Should this be public? I should not be exposing this kind of functionality to the outside world, but, well, it seems like it would be pretty useful to have a getMax method. Right? What should it return, though? The actual value stored at that location. So this dot get max node rooted at the entire tree's root dot get value. Dot get value. There we go. And return it. So this is the kind of thing that you expose to the outside world. You put things of type T into your tree, you should only expect that things of type T come out of your tree. All right? And again, I'm leaving the rest of that as a to-do for you. But that's deleting. Questions on binary search trees? Otherwise, oh yeah, go ahead.
How would you print out all the numbers in order? Or like
Good question. So here we built this tree last time, right? And how would I go about printing this in order? Yep. What was it called? An in-order traversal. That's why we call it in order, right? We do everything in the left subtree, which is less than this root first, then the root, then everything over here, which is greater than the root, and that's an in-order traversal. And that's why we call them in-order traversals. All right. So, let's see. Our motivation here was to in fact, let's go all the way up to the beginning here. We're in a quest, right? We're in a quest for a data structure that can hold elements and provide efficient CRUD operations. That is retrieval, insertion, and deletion, right? Are we there yet? So, consider this tree, right? If it's full, if a binary tree is full, then it has the potential to have a depth, which is going to be order log n. And all of our operations that we've developed so far are going to be proportional to the depth, because you have to find the node first with all of them. And then finding the maximum, that's just traversing. I mean, you're never going to go past the tree at any point. So everything is going to be proportional to the depth. If you can guarantee that the depth is going to be logarithmic because it's full, then we've accomplished our quest, and we found a data structure that provides order log n operations on insert, retrieve, and delete. Right? Have we achieved that though? Tell me about this. Tell me about this binary tree, binary search tree. It is indeed a binary search tree. It just there's no left child anywhere. It only has right children. ... 100. What's its depth? I went by tens, so its depth is technically it's 9, right? There are 10 nodes, but the depth is measured as the length of this path. So the depth here is 9. Now, if I just did this generally, right? ... n, and I followed that same pattern all over the place, then the depth would be n minus 1, or order n. So we've not achieved our goal, right? Because we can have skewed trees, trees that are not balanced, trees that are not full. Right? That's okay though, because if we have a situation like that, we can, I'm just going to do a 3-node tree here, right? It's skewed all the way to the right. What we can do is what's called a rebalancing. And this goes beyond the scope of this course, but I just want to show you what the idea here. So put your chain, which this is basically no better than a linked list, right? Put your chain on a hill here. And then imagine somebody over here pulling the chain this way. In other words, you're going to end up pulling the chain over the hill, and you'll end up with a tree that looks like this. Right? On that hill. Guess what? It's perfectly balanced, right? As all things should be. And if you have this rebalancing kind of operation when you insert stuff and you delete stuff to ensure that the depth is always going to be order log n, then you've achieved your goal. And there are plenty of implementations that do that. They're called balanced binary search trees. Again, it's not something that we're going over. Oh, whoa, come on. There we go. There we go. So, balanced binary search trees are not necessarily balanced. But there are AVL trees, there are 2-3 trees, and there are generalizations called B trees that are used in a lot of database systems. Red-black trees, et cetera, heaps. And if you just look at balanced binary search trees on Wikipedia, you'll come up with like a dozen different implementations. All of them internally rebalance somehow to achieve that logarithmic or full depth, right? They work efficiently by rebalancing the nodes. That goes beyond the scope of what we're going to do here. Instead, what we're going to do is we're going to look at things called something called a heap, right? So alternative, a heap. Right? And unfortunately, we're going to end today, and so we will have a lecture on Thursday. It's just a course wrap up, but this module does end today, so we won't be able to go into too many technical details or an implementation, but instead I'll show you applications of heaps. All right? A heap is a binary tree such that has the following properties. So first of all, it is a full tree. All nodes are present at all levels except possibly the last level, which is full to the left. Right? And I'll show you what that means visually over here is that it looks something like this. Right? It could be a full tree, in which case all of the nodes are there. Or it could be that it's a full tree except for that last level, which means that it would be full all the way to the left. There are no gaps, right? There are no missing nodes here. That fullness property guarantees that the depth is going to be logarithmic. Right? The other property is that it is this is the fullness property. The other property is that it has a heap property. It also has the every key in every node is greater, that is a max heap. Oop. Come on, max heap, or less than, that is a min heap, both of its children. Right? So to understand that, I'm going to actually give you a heap now. Let's go ahead and go with a new one, and then heap. There we go. So this is a min heap. You can see that it's full, except for the last level, but that's full to the left. Right? So we've got the fullness property, which guarantees our depth. But now it's not a binary search tree, right? If I wanted to search this thing for a particular key, and I could only start at the root, right? Would I know that it's in the left subtree or the right subtree? Like if I wanted to search for 72, right? All I know is that both of its children are greater than this key right here. I don't know where anything lies. So I've got 72 on this side, but I've got 45 over here, right? There's no rhyme or reason as far as where things are located. But every node is less than both of its children. 50 is less than 60 and 53. 40 is less than 65 and 45. Right? 45 is less than, well, it doesn't have any children, so it doesn't matter. Right? That's the heap property. Here's what a max heap looks like. Every node is greater than both of its children. Right? 40 is greater than 16 and 11. 75 is greater than 45 and 33. It doesn't matter if you consider min heaps or max heaps, because you're doing this ultimately with a comparator. And if you want a min heap and you have a max heap implementation, just switch your comparator, right? Just flip your comparator and you've got the other implementation, okay? Make an observation about this min heap here. Why do we call it a min heap? Where is the minimum? Right at the root, right? So that's our first, those are our two observations. Because of the fullness property, observations, right? Due to the fullness property, the depth is guaranteed to be logarithmic, right? So we've achieved that one of those goals that we wanted to do. That all of our operations, if they are with respect to the depth, then they're going to be logarithmic, at least on heaps. All right? The second observation is that the min or max is located at the root. In other words, we have easy access to the minimum or the maximum. Right? So this means that we can roll a heap into two basic operations. We can exploit this structure for two efficient operations. Get max or get min, which I'll go with get max. So we're talking about a max heap, right? And insert, right? We can put stuff on the heap, but we can only take out one particular element, the maximum for a max heap, right? And I'm switching to this visualization over here, okay? So we're looking at max heaps. How do we go about doing that? First of all, before we do that, why does this look like a heap? Why do these things look like heaps? It's a pile, right? What is a heap? It's a pile. And if you were to throw something on top of the pile, add it to the heap, would you necessarily, I mean, you're just gonna throw it on the pile. Is there any guarantee on where it ends up? If it's just a mess of stuff, right? Well, no, it could end up at the top, or it could end up trickling down or something like that. Or you could just throw it, you know, and make it a wider heap or something like that. Right? It could end up trickling all the way down. So how do we insert stuff so that those two properties are still satisfied? How do we add something onto this heap and ensure that the fullness property is still satisfied and that the heap property is still satisfied. Let me go back over here, and let's suppose that I want to insert, I don't know, let's insert 25. I don't even know if that's not in there. Right. Now, if I were to do it like I just visually kind of implied, where I throw it on top of the heap, right? In other words, I put it right here. I have 1 and 25 now. Well, I can't have a node with 2 elements in it. One of these things has to be kicked out, right? So 25, where would I put that?
That's a good question.
I could go left or I could go right, right? Now, if you only ever see, let's see, if you only, come on, if you only ever see the node and its 2 children, do you know where the gap is? That is, if I were to insert it and it trickled all the way down over here, and it ended up being the new right child of 45, now I've got a huge gap. The fullness property is no longer satisfied. So if you only ever saw the node and its 2 children, do you know which way to go? Nope. So let's go ahead and rethink that. Don't throw it on top of the heap like you would like a pile of clothes or something like that. Where should we throw it to ensure that the fullness property is satisfied? At the bottom. Right? Now the fullness property is the next available spot is what I did. So at the lowest level, all the way to the left. Right? Now the fullness property is satisfied, but is the heap property satisfied? Nope, this is a min heap. Where should 25 be? 25 is not less, or 53 is not less than 25. That's okay, we can fix it. How would we end up fixing it? Swap these, right? Promoting 25 up, taking 53 down. 25 is now here. Is the heap property satisfied? Nope. 25 is less than its parent, 50. So swap it again. Now I've got 25 here, 50 here, and 53 here. Right? And now the heap property is satisfied. Let's see it in action over here with a max heap. Okay? So let's go ahead and insert an element here. And I will go ahead and insert 101. Okay? Where's it going to end up? Before we go through the simulation, where is it going to end up first? A new level all the way to the left. So the left child of 16. And pause. There we go. Left child of 16. The fullness property is satisfied, but the heap property is not satisfied. Because remember that this is a max heap. So we proceed to compare it with its parent and see that that the heap property is not satisfied, and we end up exchanging. We continue doing that until we go all the way up to the root, at which point we're done, or the fullness property, or the heap property is then satisfied. For example, if I inserted, say, 90. All right, stop. Right child of 40. It ends up getting promoted up 1. But then when we compare it to 92, now the heap property is satisfied. It didn't heapify itself all the way up to the top. And that is the verb. We do call that heapification or heapify. Right? Because we like making up words. Yeah? So that's a good question on how we actually implement this thing. Right? Hold off on that until we get the other operation. So what's the other operation? Get and remove the minimum or get and remove the maximum, depending on if it's a minimum or maximum heap. Well, I can go ahead and get it because it's right at the top there, right? There. I've saved it off, and I'll return 1 to you after I'm done. However, there's a gap here. Right? The fullness property is no longer satisfied. So what I could do is I could start promoting children up, right? Between 5 and 30, which one should go up? 5, right? So between 50 and 55, which one should go up? 50. So there's 5 has been moved up. and 50 has been moved up. And now there's my gap right there. Now between 60 and 53, which one should be moved up to satisfy the min heap property? 53. Problem now, what? Gap. Can't have that. So once again, let's try to focus on the fullness property first, and then we'll worry about heapifying it and fixing it. All right? So 1 is gone. What could I replace it with so that the fullness property is satisfied? 63. Right? Take the last available element. Right? It has no children, by definition. Therefore, we're just taking it off means that the fullness property is satisfied. Now, is the heap property satisfied here? Nope. Because 63 is greater than 5 and 30. So now I start exchanging it with its children. 5 comes up here, 63 goes down here. 50 comes up here, 63 goes down here. Then 53 comes up here and 63 is down here, and the heap property is now satisfied. Again, visualizing this, extract max means that we promote 40. Hopefully that wasn't too quick, right? We take out 101. We need to replace it with something. We replace it with the very last element. Then we need to heapify down. In this case, we exchange it with the maximum of its 2 children because it's a max heap. And the maximum of its 2 children, 90. And at that point, we don't have to go all the way down to the leaf because the 40 here is greater than 16. Excellent. Now back to your question on how do we implement this? Right? So if you want a node-based solution like this binary search tree over here, it is possible to do it. Read the book. It involves a lot of mathematics because if you start at the, not a lot of mathematics, but exponentials and stuff like that. Right? If you start at the root, the essential question that you need to answer is, where is that next available spot? Or where is that last element? And so just given the root, though, you have to know, well, is it in the right subtree or is it in the left subtree? Right? And using some basic math and keeping track of how many elements are in the heap, you can do that. You just traverse, oh, it must be in the right. Okay, I'll go down. Now I'll ask, is it in the right subtree or the left subtree? All right, it's in the left subtree, and then you just continue going down all the way just using math. All right? It is possible to do that. But even easier than that, as the visualization is hinting at here, take a look at those red numbers. Right? Those are indices. Read top to bottom, left to right. The root is at index 1. Its left child is at 2, its right child is at 3. Let's visualize that over here. Right? So here's the 92, 90, 75. 90, oops. 90, 92, 90, 75. What else was there? 40, 11, 45, 33, and 16. There we go. Now, these had indices 1, 2, 3, 4, 5, 6, 7, 8. If I'm at this node right here, I need to determine where's my left child, where's my right child. So 90, its left child is 40, and its right child is 11. There's its left child, there's its right child. How did I get that map? Reconnection successful. Excellent. Wow. OBS is awesome. OBS can, well, yeah, there, now we're back up to 2000K. All right, now we're good. All right. Wow, good job, OBS. All right. Excellent work. All right, so to go back to where we were, remember that we're at 90 here. I need to know where its left child is, where its right child is. Look at those indices. Right? If I have 2, then its left child is at 4, its right child is at 5. And by looking at this after a while, you can find a pattern. If I'm at index I, then where's the left child? And where's the right child? If I just went 2 to 4, then it's going to be where? 2i. Right? And what if I go from 2 to 5? It's going to be 2i plus 1. Where's the parent? Oh. Come on. It needs to wake up. Oh, whoa. It's a... Come on. I'll reconnect you then. OBS is... Oh, no. OBS is dying too. All right. I spoke well of you too soon, apparently. All right. QuickTime gets restarted. Oh, wow. It slowed down to a halt here. No, I'm using QuickTime to just share the screen basically. Otherwise, you'd have to pay like $15, $20 for some app to share the screen. All right. I don't want that. All right, it seems to have recovered now fully. Yeah, my mouse is moving nice and smooth. There we go. All right, sorry, there we go. So the left child is at 2i. The right child is at 2i plus 1. Where's the parent? All you have to do is reverse this. What's the reversal of 2i? I divided by 2. Right? If it's 4, how do I go back? Divided by 2. However, if it's 5 and I divide by 2, I get 2.5, so that's all right. Just take the floor, or truncation. Right? And that is an efficient way of implementing a heap. What's not an efficient way of implementing a heap is, reverse that. That's so convenient that you might, that a Gomer might immediately think, why do I need nodes at all? I don't need a node class. I could just do this for binary search trees as well. Right? Okay, and Gomer proceeds to use an array to store a tree, a binary search tree. Now think about this. If there's 10, 20, 30, ... down to 100, and 110, just so that the depth is a perfect 10. Right? How big of an array would you need to store that thing? Remember, you're going to end up having a whole bunch of gaps over here. So how big is your array just to store 11 things? 2 to the 10 plus 1 minus 1. Right? So, and most of them are going to be empty blank nulls. Right? So no, you cannot, you can only use this trick because of the fullness property. Right? And that's the only reason that it actually works. But it's really nice, right? And by the way, we usually burn 0. Otherwise, you would have to say subtract 1 off of everything, right? And then it doesn't look good, right? All right. Cool. Now, let me go ahead and restore my min heap here. There we go. And now let's do one application of this thing. So presumably I've created this heap by putting stuff into it and heapifying along the way, et cetera, et cetera, et cetera. What if I start taking stuff out one by one using get min? First of all, can I do an arbitrary search on a heap? If you wanted to search for 65, could you do it by starting at the root? Do you know to go to left or to go to the right to find 65 down here? Nope, no information. So in other words, in order to find something arbitrarily, you're going to end up having to do a BFS or pre-order or in-order traversal of this thing, whatever, right? Which is going to be linear, right? If you want efficient search, retrieve, update, destroy, then you're shopping for a different data structure. You're shopping for a balanced binary search tree, right? Let me double check. Okay, it says it's going. Hopefully, it is going. I don't know if it is or not. But anyway, any case, let's go ahead and start taking stuff out. If I take out the minimum, then that's going to be 1. If I did it, and then of course it'll fix itself, right? 63 will end up being put up at the top, and then heapify down, and then 5 will be in the new minimum. Do it again. 5. Right. Do it again. What's the next thing that will come out of this heap? Where is it? 30? Yep, 30. What's the next thing that'll come out of this heap? 40. What's the next thing? There is a 45. Then 50. Then 55. ... Tell me about that sequence. It's in order. It is sorted. Right? To get each one of these, what kind of operation did I need? As a get min, but everything is proportional to the depth, and the depth has a guarantee of log n. How many elements are there total? N. So putting stuff in, taking stuff out seems like a good way to sort. What does it look like? It's called, by the way, heap sort. And I'll forgo the input-output. The input is a collection A, A1 through AN. The output is A sorted, blah, blah, blah. What I'll do is I'll establish a min heap here. I'll initialize a min heap. Then for each element, AI, in the collection A that you're trying to sort, put it in there. H.insert AI. Now for each element that you put in, take it out. Right? For I running from 0 up to, actually, 1 up to n, right? A sub I will now be reset to H dot get min. Right? And then you're done. Right? Why? Because if you put stuff in and then you take it out, the properties of the heap means that you're always taking out the minimum, then the next minimum, then the next minimum, then the next. Right? This is executed n times, and that each operation, that is insert operation, is order log n at most. So in total, this entire thing is going to be n log n. Likewise, you execute this n times, and each operation there is log n. Right? So in total, you've got n log n plus n log n. Does that change it? 2n log n? We ignore constants, so it's going to be order n log n. In other words, it's a guaranteed fast sorting algorithm. But it goes all the way back to the beginning of this course. One of the themes of this course is that smart data structures and dumb code are a lot better than the other way around. Right? In other words, smart, clever code, like say quicksort. That's clever, right? It's got this nice partitioning thing where it pivots around this pivot element, and then it's got this recursion, and then your choice of pivot element, you can fine tune that. Merge sort is also clever code, right? Clever, smart code, because it's got this nice merge method that if you've got a sorted list and a sorted list, you can zipper them up pretty easy, right? Clever, smart code. This is dumb code. It doesn't get any dumber than that. Put stuff in, take stuff out. Put stuff in, take stuff out. Smart data structures and dumb code are a lot better than the other way around, right? Because your data structure is doing all the heavy lifting. Your data structure is doing all the powerful stuff. Right? And once you understand data structures, then you've got all of this library out there of data structures that you can bring to bear on a problem. In Computer Science 1, what's the first thing that you ask when you're approaching a problem?
How do you do it?
Hopefully that's the second thing. Oh, what? You're trying to solve the problem, right? So what's the first thing? Remember, think being lazy. The best engineers are the laziest engineers. Is it already solved, right? Is there an off-the-shelf solution that I can bring to bear to this thing? After Computer Science 2, you should be answering or asking a similar question. How do I solve this problem? What data structure could I pull off the shelf that would solve this problem for me with super dumb code? Put stuff in, take stuff out, right? Stacks, queues are another example, where if you use a stack and you get a pre-order traversal, same code, put stuff in, take stuff out using a queue, gives you a BFS traversal. Right? Very, very powerful stuff. Computer Science 3, I also have a quote. In fact, we have enough time. I'll just pull up the exact quote that kind of mirrors this theme. Documents, syllabus. No, here we go. There we go. Charles Learson, I don't know who, Learson, I don't know, whatever. If you want to be a good programmer, just program every day for 2 years. Good programmer. If you want to be a world-class programmer, you can program every day for 10 years. Or you could program every day for 2 years and take an algorithms class. And algorithms class, I would add in that algorithms and data structures class, right? I don't think that he'll complain about amending that. Because again, smart data structures and dumb code are a lot better than the other way around. You can solve problems so much quicker, so much more efficiently if you know, that's a standard stack kind of base solution. I'll just pull in a stack and I'm done. Right? Question or?
Was he advertising for an algorithm?
I don't think so. I don't even know who he is, but.
Also, I missed the heap sort. I was checking to see if you were still alive.
Oh, okay. There we go. Heap sort.
Or like
You.
the visual representation of it.
Well, okay, this visual. So the visual here is that, you build the heap, and then you simply just take stuff out. Right? You're always taking the minimum. Right? Once that's gone, then what's the next minimum? 5. Once that's gone, what's the next minimum? 30. Right?
And then it keeps on that order, like
In fact,
middle, left, right.
here you go.
Right.
I'm not sure exactly what this looks like. 92, 16, or 90. Then it fixes it, and then we extract 90. Right? And then we extract the next maximum in this case because it's a max heap. The next one, 45. And then the next one is going to be 33, or sorry, whatever that was. Right. And I'm just going to go ahead and pop all the way to the end here. The final sorted order is 11, 16, 33. This was pre-pending probably. So it's still in ascending order even though it's a max heap. That's just because it started its for loop at n. So you could go with n down to 1. Well, no. I mean, if you want to, if you have it sorted ascending, if you want it descending, just reverse it. That's way easier.
Well, no, I just mean that does it follow like a set pattern? Like I know sometimes it's like middle, right, left.
No. There's no. It all depends on entirely on the elements. No pattern. Right. Okay. Any questions? Otherwise, heap sort, super nice. Another application of heaps is a priority queue. So a queue normally, first in, first out. Right? It's a nice line, but you can have line jumpers, right? The classic example is Disney World. There's a fast lane, right? So if you pay double or something like that, you can jump to the head of the line. Problem now is that that fast lane line is just as long, just as frustrating as the others, right? But you can have individual priorities. So in the Unix system, there's this niceness level where you can a niceness level of 1 to 20, and a process niceness level can be set low so that it says no, go ahead. I don't have a high priority. Everybody else can go ahead of me. 20 says that no, I am absolutely essential. I'm an essential process. Let me jump to the head of the line. So you can imagine 1 through 20, right? A priority would mean that somebody gets thrown in the mix. If you're priority 5, they don't get to go all the way to the front of the line, but they don't have to go to the back of the line, right? They go somewhere in here, right? Which is kind of what you're doing with a sorted set, or a sorted list, I should say. Sort of, right? But the idea is it doesn't matter where they go in line because they're calling the person with the highest priority next. So it's more like a deli or something where you take a number, right? And but that number is not the next number. That number is like a priority number. Oh wow, I'm lucky I got next, right? Versus somebody who gets a low priority number and then they have to sit and wait as more people come in and they get higher priorities. They might literally starve in the back because they're not getting their sandwiches. And we do say that processes starve if they don't get to run, right? They don't get the resources that they need to run, and then they sit there and they just sit there idle, non-busy, and they starve. It's called starvation, right? What? Oh, the DMV, they go in order, right? First come, first serve. I think. I don't know. They're online now. Who cares? All right. So next time we will go ahead and finish out the course with the retrospective.